Hello everybody, my name is Bettina Koch and I study at TU Wien, and today I will present you my topic Ink Development for the Fabrication of Digital Materials with Increased Fracture Toughness. So our goal is to 3D print a material which provides a high tensile strength, a high E modulus and a high glass transition temperature, but also a high elongation at break and a high toughness. So it should look like this red curve in the stress strain diagram here. But the main issue is that most photopolymers yield brittle materials like this green curve, and if you increase the elongation at break, you mostly reduce the tensile strength and therefore their toughness is hardly increased. And our strategy to solve this problem is the fabrication of digital materials. So what are digital materials? They are a composite material where a primary matrix material is printed by lithography-based additive manufacturing technology, and the second material is selectively added by inkjet printing. So this hybrid process was developed by TU Wien, and you can see how it works in this video. First, the wet is coated, the building platform lowers down, and the matrix material is printed. Then the building platform moves up, rotates, and the ink is applied by the inkjet printer and is then cured by an LED. And these two steps are repeated until the whole part is finished. And in this way you have a material where every point is either unmodified, then it's the matrix material, or modified, then it's the ink material. And you can see you can have discrete inkjet droplets like in this picture, but you can also have overlapping inkjet droplets in one direction, then you get fibers, or in two directions, then you get full layers. And what is our motivation? Why do we do that? It's based on natural toughening mechanism. One example is nacre. With its unique brick and mortar structure out of minerals and proteins, it is possible to get crack deflection and branching of cracks, and in this way nacre is a quite tough material. And another example are glass sponges. Here you have laminated structures with alternating silica and organic layers, and the crack propagation stopped into the soft layer due to the shielding effect. So what is the shielding effect? It happens due to unequal mechanical properties of the soft and the hard material, and it's effective if the ratio between the elastic moduli of the two materials is at least 5 or higher. And we want to use this shielding effect to toughen our materials. So we have a matrix material which should be hard and should provide a high tensile strength, a high E modulus and a high glass transition temperature. And we have a soft ink which should have a high elongation at break and increase the toughness of the matrix material due to this shielding effect. And I'm working on the development of this soft ink. And here are the requirements of the ink in detail. So we want to have a glass transition temperature lower than room temperature, because then we have a low storage modulus at room temperature and a high difference to the matrix material. As I already said, also the elongation at break should be high. Of course, it should be stable in storage to prevent gelation of the ink in the printhead. Another important point is the processability. Here low viscosity is important because by inkjet printing you need a viscosity that is lower than 20 millipascal seconds, while we can only heat it up to 60 degrees C. And also the surface tension should be suitable according to the manufacturer of the printhead. It should be around 30 millinewton per meter, and out of these parameters you can calculate the Ohne-Sorge number, which should be between 0.1 and 1 to get a jettable material. Also the reactivity is important, so we want a fast photopolymerization because the ink is only irradiated for a few seconds. So if you are not so familiar with photopolymerization, here is a short introduction. First you have an initiation step where a photoinitiator is cleaved by the irradiation of light and two radicals are formed. Then these radicals can add to the double bond of a monomer, and a new radical is formed on the monomer molecule. Then the second step is the propagation, where the new formed radical can add again to a double bond of a monomer, and in this way a chain is formed. And you also have termination reactions like recombination of two radicals and disproportionation. So if you have a monofunctional monomer, like in this propagation step, you get a chain if you do the photopolymerization, and therefore a thermoplast-like material. If you have a defunctional monomer, every molecule can cross-link, and you get a highly cross-linked network, and therefore a thermoset material. And if you have now a mainly monofunctional monomer and a low amount of defunctional monomer, you get a weakly linked network, and this should be like elastomer, and this is our approach for the soft ink. So I developed a soft ink based on cyanoethyl acrylate with a low amount of crosslinker inside, and we wanted to compare it with the commercially available ink Tango Plus from Stratasys. So first I measured the viscosity, and you can see here that the cyanoethyl acrylate in Turkish has a much lower viscosity than the Tango Plus. At 25 degrees C, the viscosity is only 5.6 millipascal seconds, while Tango Plus shows a viscosity of 106 millipascal seconds. So for the Tango Plus, you would really need the 60 degrees C because here the viscosity is only 22 millipascal seconds. The next characterization was the storage stability. Here viscosity measurements after certain time intervals were conducted, and both inks are stable in the fridge and at 50 degrees C, so this is fine. Furthermore, I investigated the photoreactivity via photoreology measurements. These are oscillation measurements during light exposure, and in this way you can record the storage modulus and the loss modulus, as well as the double bond conversion over time. And here you get a lot of parameters which can be compared, and I will show you two important parameters for the photoreactivity. One is the TG, this is the time until the gel point is reached. This means the time until the material gets from a liquid state to a solid state, and the cyanoethyl acrylate needs only 0.7 seconds to reach the gel point, while the Tango Plus needs 2.6 seconds. This means here the cyanoethyl acrylate is 3.7 times faster than the Tango Plus. And another important parameter is the time until 95% of the polymerization are finished, the T95%. And here the cyanoethyl acrylate needs only 3.5 seconds, while the Tango Plus needs 19.1 seconds. And this means in terms of T95%, the cyanoethyl acrylate is 5.5 times faster than the Tango Plus. Then DMTA measurements were conducted. You can see both materials have a very low glass transition temperature, lower than room temperature with 10 and 5 degrees C, and therefore also the storage modulus of both materials at room temperature is very low, lower than 1 megapascal. So that's fine. And also tensile tests were conducted, so you can see in the diagram the best out of 6 measurements, and the X marks the average value. So both materials have a high elongation at break. The average value of the cyanoethyl acrylate is 210%, while the Tango Plus shows 174%, but yeah, both materials are fine in terms of elastomeric behavior. But in summary, I can say that the cyanoethyl acrylate is easier processable due to the lower viscosity, and it's completely outperforming the Tango Plus in terms of photoreactivity, which is important for our application. Then we use the cyanoethyl acrylate based ink to print a digital material. Here a matrix material was chosen and 25 micrometer layers were printed, and then inkjet 0, 1 or 2 inkjet cycles were applied. So 0 means there is no ink and this is only the matrix material as reference, and then 2 different amounts of ink were added. And nano indentation measurements of this printed material were conducted, and here force controlled measurements were done because you have a fixed force, and then you get different penetration depth depending on the material, and out of this penetration depth the software can calculate the E-modulus and the hardness of the material. So in the following I will only compare the E-modulus because both show the same trend. And you can see first the pure materials were measured. So the pure matrix has an E-modulus of 5 gigapascal, while the pure ink has an E-modulus of 7 megapascal. This means there is nearly a factor 1000 between the two materials. And then the printed digital material was printed. Here the sample with 2 inkjet cycles is shown. And you can see there's only a factor of 2 or here 3 between the soft and the hard phase. And this is lower than I said in the beginning because we want to have a factor of at least 5 between the layers. And we think that the reason for the not well separated layers is the diffusion of the ink into the matrix due to the polar nitrile group of the cyanoacyl acrylate. And we also did swelling tests where we put a molded matrix plate into the cyanoacyl acrylate and measured the mass increase after 22 hours at 50 degrees C. And here the mass increase was 11.5%, and this is quite high. So we think this is the reason for the not well separated layers, but nevertheless we did further tests. So we also looked at the structures via LSM measurements. Therefore we added a fluorescence dye to the ink to make the layers visible, and you can see here in the pictures the red inkjet layers are well visible. There's not always the same distance between the layers, but it looks quite nice. And we also did tensile tests to see if it is possible to toughen the matrix material. And you can see here, the higher the amount of ink, the lower the tensile strength, but it's only decreased by 14 or 21% if you add 1 or 2 inkjet cycles to the matrix material. But the elongation at break can be increased much more by 24 or 106%. And since the elongation at break increase is higher than the tensile strength decrease, it was possible to increase the toughness by 19 or 117%. So in summary, I want to say that we use the concept of digital materials to combine two materials by lithography-based additive manufacturing technology and inkjet printing. And we do that because we want to combine different material properties, and it's a strategy to increase the fracture toughness of a material. I developed the cyanoacyl acrylate-based ink, which is processable, stable, has a high photoreactivity, a low glass transition temperature, and a high elongation at break. And compared with the commercially available Tango Plus, it's quite similar in most properties, but it's really outperforming it in terms of photoreactivity, which is important for our application. And then we use the cyanoacyl acrylate-based ink to print digital materials. Here the sample with 2 inkjet cycles was performing the best, and despite the factor between the E-modulus of the hard and soft phase was only 2 to 3 instead of the 5 which was desired due to literature, toughening was possible, and the tensile strength decrease was maximum 21%, while the elongation at break increase was up to 106%, and in this way it was possible to increase the toughness of the matrix material up to 117%. So our goal was reached, the matrix material was toughened, and yeah. Thank you for your attention, and I'm looking forward for your questions.